I introduce Michael Perry. Okay, what's going on? So Michael Perry is a professional software mathematician. His career has ranged from software consulting to designing and architecting software of all types. He's an experienced Pluralsight course creator with extremely highly rated courses on developing with entity framework, distributed systems, and even cryptography. He's also He's also a well-versed community speaker with dozens of talks under his belt. Not to mention the host of the QED Code podcast. Recently, he's been expanding his work into writing as the author of The Art of Immutable Architecture, Theory and Practice of Data Management in Distributed Systems, as well as developing a groundbreaking piece of software aiming at becoming an application-agnostic backend for web applications, right? So for those who that was just a bunch of words, this is huge, okay? So it'll all come through in just a little bit, so stick with us. So to say the least, Michael knows what he's talking about. He's been in the industry probably for longer than I've been in formal schooling. So with that said, Michael, welcome. So
Hey,
glad.
Conrad. Good to hang out with you.
Yeah, do you want to kind of maybe fill in any gaps that I created just there, or anything like that? Anything you want to add?
Yeah, I just want to kind of double tap on the software mathematician. That's a title that I gave myself because I recognize that software is applied mathematics. And yeah, if you look out there, you'll see plenty of people who have contributed an awful lot to computer science. So Leslie Lamport is one of my heroes, and Mark Shapiro has written a whole bunch of math papers on CRDTs, which is a specific type of data structure in computer science, and so the idea of software as a form of mathematics just is in my bones, and so yeah, I donned that label of software mathematician, and so yeah, even though there are those out there who do that better than I do, it's a thing that I own, and I love doing it.
Well, I mean, you walk into any room, somebody in that room is going to be a little bit better than at some topic, how arcane or how general, this is just the life that we live. So essentially, you're building off of the work that's come before you. I mean, this is a very human thing, right? And instead of applying it to theory or furthering, math just for math's sake, you're actually taking some of these principles and applying them to your software development practices.
Exactly. Yes. Okay. Yeah. So with a lot of people, when they hear, like people will ask, do you have to be good at math in order to write code? And that's usually followed by a whole bunch of assurances that no, you don't have to worry about the fact that you didn't do well in math class in high school. You can still be a good coder, which is absolutely true. But the fact is, the math that you learn in high school isn't what math is. What you do in software when you are writing code, when you're refactoring code in particular, that is math. So if you're good at software, you are good at math. It's not the sort of math that you did in high school. So take your favorite refactoring tool and you say, okay, I'm going to select some lines and I'm going to extract this bunch of code as a method. It's going to generate a brand new method. It's going to take all of the parameters that were declared above your selection that are used inside of your selection. It's going to make those parameters. It's going to take all of the values that you generate in that code and that's used later. It's going to make those the return statement. So basically, it's just putting parentheses around a bit of math, and then it's literally doing the factorization of that equation. And so it's applying properties that we know from our math classes, like the distributive property and the commutative property, and it's just running those operations symbolically over the code in question.
Right. So essentially, these refactoring tools, it's interesting because I had always thought of refactoring as more of a communication than following a line of formal proofs.
Actually, a conversation is exactly what math is like. to a practicing mathematician. They are having conversations with other mathematicians, with people who've written papers before them. The papers that they're writing are now conversations that are that others are going to build on. So actually, the conversation metaphor is exactly what I love to think about. I love to think about myself having a conversation with the compiler. People often talk about fighting the compiler. It's not a fight. It's a dance. It's trying to figure out what you're going to have for dinner. It's a conversation, and it's a conversation with other people who are working on that project because they're going to be reading your code.
So, so what is a compiler? A compiler is essentially something that goes through. It has a set of grammar, and essentially it looks at your code, because what is code? It's just a series of instructions. So let's say we take a paragraph. If we were going to compile like a paragraph, like, can you kind of run us through like what exactly is happening there, and kind of why this is important? Because some people want to fight the compiler, which like fighting gravity, like you
right,
can't.
You're not going to win.
Whatever. Yeah. So if you wouldn't mind, just kind of dive into that a little bit deeper.
Yeah. So code isn't a sequence of instructions. Code is intent. It's an expression of what you want to happen. And some languages do express intent in terms of step 1, step 2, step 3. Those being the more procedural languages. But some languages express intent more in terms of equations, more in terms of a mathematical expression, and even the languages that we're most familiar with have a mix of both of those. So you are in fact expressing your intent in terms of, like, I've got this class. It has a property. The property has a getter, and this is an equation that it's going to compute when it returns that value. So my intent is that the person's full name is going to be their last name followed by a comma followed by the first name. That's the expression of intent. And so when you're having this conversation with the compiler, you're telling it what your intent is, and then you're waiting for it to respond with whether it understands that intent. And then if you take it one step further, whether that intent has some implications that are going to be important to you. So the first thing is, the compiler says if it's syntactically correct. So can I understand your intent just from the words that you've used? But then it does the next level up. Does it make sense to the type system? Is it, do I understand that your intent from the point of view of, if you have this thing that you said that you wanted to have, can it perform that operation? Can I say, person dot drive and pass in a car? Does that intent make sense? Do those objects go together in that way?
So this is essentially, you basically guarantee that the intent of the programmer gets represented or manifested by the compiler at the very end. I'm wondering, where did this idea come from? Why is this important? And why is this important, really?
Yeah. Okay. So it's important because you need to understand the implications of what you say and you intend. You need to understand, have you overconstrained your system? To bring it right back to mathematics, if you say I want to have an equation or a system of equations that represents the flow of a fluid through a pipe, and so okay, the amount of fluid coming in is equal to the amount of fluid coming out. Okay, that's one equation, and the flow rate is going to be restricted by the diameter of the pipe. Okay, we can write another equation for that, and you write a set of equations. If you end up with a set of equations where the number of equations is exactly equal to the number of variables, the number of unknowns, then you have a system that has 0 degrees of freedom. So
it's solvable.
it's solvable. You
can
find
figure it
the
out.
exact
Gotcha.
answer. If you have fewer equations, so fewer constraints than you have unknowns, then that means that that it has multiple degrees of freedom. So if you just have one fewer equation, like you've got 3 equations, but you've got 4 unknowns, then that means you've got 1 degree of freedom. There's one thing that can flex in there, which in a real system might mean that there's some slop. There's something that that could change over time, and as an engineer, you might look at that and say, well, I want to get rid of that slop. I want to be able to control it. So you add another constraint.
Interesting. Yeah. So the metaphor here might be you've got a case of Dr. Pepper, right? And instead of having 12 Dr. Peppers, because there's like 12 constraints applied, a few of those are out. And so when you're talking about this slosh, like imagine you have this case of Dr. Pepper and there's holes in the thing. And so these cans are allowed to slosh around. And so it's like you can dynamically change the structure of like the soda cans or the case that holds the soda cans such that there is no more sloshing, right?
Right. Yeah. So you constrain it to where you get exactly the number of degrees of freedom that you expect to have in your problem. And those degrees of freedom, those extra places where things can move around that don't actually represent real things in your problem, that's where bugs can creep in. So you expect that when you run the system under normal circumstances, it's going to follow a particular path. It's going to do certain things. And if the code allows for other degrees of freedom, other configurations of the variables, other ways in which it can move, then there may in fact be a situation that pushes it into those other areas. Yeah. And if you haven't tested those areas, there might be a bug over there. So yeah, limiting the degrees of freedom to exactly what you intended is one of the ways in which this is a really powerful metaphor for writing software.
Well, so the first question, and maybe you can answer it like last, is why the heck is everybody not doing this? It seems so. This seems profound. This seems like an invention, literally. And basically, so for those who don't kind of understand, the way that software is currently developed is at the end of the day, it's just reads and writes. You write data and you read data. You transform it in some way, and in the way that. So basically, that's all it is. All these websites, all these apps, you write data and then you read data, you transform it in some way. So basically, as a software engineer, what you might do is you might design the database, and then you'll design kind of the back-end logic that handles these reads and these writes to the database. So maybe you'll have a set of instructions that says, store this person's contact information, their name, their date of birth, and their hair color, right? Mm-hmm. And so you have some instructions that do that. You have a database that stores this information, and then essentially you have telephone poles that connect the database to the API, and they just shuttle information back and forth. And if you've built this once, you've built it 1,000 times, or maybe said better. If you've built it 1,000 times, you've pretty much built one thing 1,000 times. There's no difference. And when I came across Jinaga, I was actually blown away because you actually abstract like the repeated parts of software development into just configure it. You basically just define the configurations. You define the specs that you need, and essentially the system builds itself. And this was profound. So maybe you can kind of walk us through where this problem came from, or when you decided, like how you decided, and what's that story there? Like, how did this come about?
Okay, yeah. So let's kind of take it back to the idea. Originally occurred to me when I was working on a frequent diner program for a hospitality services company. So yeah, we're building the system where people can get a card that they can bring into a restaurant, or maybe they bring it to a bar, and then every time they buy a beer, it keeps track of that, and they have to buy everybody's every beer in order to get a plate, and then they that gives them some discount. So we've got this idea of, okay, we've got this history of all the different purchases that this one person has made, and it occurred to me that they're making purchases at this bar, but then that other bar, but they're the same company, and so we want to take the information from different places and union that information together. And that's really hard to do if you're keeping track of information by by scratching things out and writing new things. So so if you say, okay, how many how many Guinnesses have you bought? I've got 3. No, scratch, make that 4. But then you make that same change somewhere else. How do you know that it actually should be 5? How do you union those things together? And so it occurred to me, well, things that change are really hard to sync. But if something doesn't change, then syncing is easy. I just tell you that a fact is true, and then whether you know that fact already or not, now you know that it's true. So we've just merged you've merged my knowledge into yours. You tell me about facts that you know. I may already know them or I may not, and I've just merged your knowledge into mine. And so if we do this over and over again and share our knowledge, then we have the same set of history in our heads. So that's the that's the fundamental premise of this. Replace the programming metaphor of an object with properties that you can change. You scratch them out, write a new value. Replace that with a graph of immutable objects, each one representing a certain decision. Somebody decided to purchase a Guinness at this restaurant. Somebody decided to purchase a different Guinness at a different restaurant, and so you union all of those facts together, and then what you want to do is reproduce the kinds of behaviors that we're used to in our software systems. So make it appear that things can be modified, make it appear that things can be deleted, but in fact, all you're doing is you're accruing this immutable graph of facts.
Okay, so just and I'm going to try to summarize what was just said, and please correct me where I've kind of gone off the rails. So essentially, we're sitting in a bar, and there's 2 ways to go about this, because the bartender needs to know how much to charge us at the end, right? Mm-hmm. And so there's a tremendous amount of updates and changes in these things that need to be synced across basically everybody. And maybe a better way to do this is only record the changes, right? So you only record the things that cause things to change. So honestly, it doesn't really matter. Maybe it does. But the reason that things changed, maybe that doesn't matter quite so much. All that we need to know is at the very end, maybe the bartender keeps 1 tally of everything that happened. And actually, now that I think about this is in fact how bars work, right?
Yeah, exactly.
If you want to order a drink, you don't write it on your card and then give it to the bartender and he tallies it up and calculates. Mm-hmm. No, it's you tell him, hey, we need 2 drinks, and he's like, okay, sure, and he keeps a central kind of ledger going, and essentially it would be 2 additions, right? Or 1 addition of 2 drinks, and then let's say at the end we're going to split in some fancy way. This is a little bit interesting, but the idea of splitting the tab is an additional step. Right.
Yeah. So that's an additional decision. Yeah.
Right. And so basically what you're describing is just a series of things that happened, and you can only add to it. It's like time. It's like history. It's like the things that you've done in your mm-hmm. life. You can never go back and change something, but moving forward, you can live however you'd like, and you can kind of do these things. And this is the way that life works. And you're saying that this is the way that software should work?
Yeah. Actually, this is the big lie of object-oriented programming, is we think that we are modeling the world as it is when we write an object-oriented program. But you just pointed out, this is the way that bars actually work. They don't work by having these objects with these properties that they can change. They work by, okay, I received your card. I'm going to go ahead and create this transaction. That transaction exists now, and that's the way that all businesses work. That's when you fill out an invoice. That's a permanent, unchangeable document that you now exchange with other people. And then what's the status of that invoice? Well, the invoice itself doesn't change status. It's just, has there been a payment applied to that invoice? Does some other fact exists, some other document. So
this is interesting because it seems so silly. Like, let's say everybody kept track, like these objects you're talking about, keeping track of their own internal state. And it's so weird. How did it take this long to happen? I mean, it's weird because this is how life works. So I'm just, yeah.
Well, this so far what we've described is not completely unique to Jinaga. So you may have heard of the idea of event sourcing. So event sourcing is also a system of keeping a history of the things that happened rather than the current state. So they're all immutable. In the term of event sourcing, they're called events rather than facts. But where those differ is earlier you said that that life is a sequence of these decisions. Sequence is not the right word. That's where these ideas differ. So when you are living your life, you are only experiencing the decisions that you make and then the decisions that directly affect you. But then you go and you talk with somebody else. Now they've got a different set of life experiences. Once you've told each other your stories, now you know about all of these other decisions, but they happened in parallel. They didn't happen in a particular sequence. I mean, if you get right down to to general relativity, there are no simultaneous events. There are just pockets of causality. So. Without getting all the way to that metaphysical level, even within just business exchanges, I don't need to know about somebody else's purchases and see that on some huge linear history in order to understand the effect that my purchases have. So I can boil down, I can take a subset of history just based on that causal relationship. I paid this invoice because somebody sent me an invoice. They sent me an invoice because I sent them a purchase order. I sent them a purchase order because I saw a catalog. And so those historical facts are causally related. But the things that are not causally related don't play into that particular transaction. So the unique sauce that Jinaga adds to that is that it builds a directed acyclic graph out of these historical facts so that you can work with just a subset of them.
So, and correct me if I'm wrong, a directed acyclic graph, what makes that special is that essentially there's like, well, obviously there's many paths through this kind of arcane tree structure, but the reason that, so you said directed, so directed kind of implies that there is a current or a direction of flow through this structure, and in a way it implies you can't go backwards, right? It only goes in one direction. Is this fair kind of?
Yeah, and that direction is backward in time. So I decided to pay this invoice because of the invoice. So the direction is from payment to invoice.
Right. So the effect, or whatever the effect was, they reference the cause. Yes. And so it's this kind of long chain of, oh, this happened because of that, and then this happened because of that. So it basically builds this essentially this chain of events where at any point in time, maybe essentially what you could do is you could say there was all these events happening, and you can send me the data here. Let's say this was June 14th. You can send me the exact current ledger almost of things that have happened over the entire lifetime of the system, and I could recreate exactly the state of the whole system at a very specific point in time. And so this seems to be one of the benefits of this event.
The really powerful. So that is one of the benefits of event sourcing, is that they usually have a centralized sequence of all of the events that happened in the system. But the real power of this being a directed acyclic graph rather than a sequence is that I don't have to send you the entire state of the system as of November 14th. I can send you this particular payment, and you understand the history that led up to this payment, which is very short. that can all fit in memory, just that can fit on a screen. And so you can query the graph directly to look for, well, what are the things that happened after this, and you can understand now what the state of that invoice is. You can understand what's next. So here's an invoice without a payment. Oh, the next thing to do is to pay it. And so the idea of being able to take just a subset and process that in one location, that's powerful in two ways. First of all, you can work with that subset. It can fit in a small amount of memory. But then secondly, now you have the autonomy to make decisions, add them to the graph, and you don't have to tell anybody else about them right away. It's still true. You have autonomy knowing that those decisions are going to be honored in the future. You don't have to wait for them to get on the blockchain or something.
Right.
So even if you're working with Git is a perfect example of this. So you clone a repository, you're working on a branch, you're just making commits just on your own local machine. Those commits are true. They happened. And then when you push that branch up to another remote, now other people can see that history. Meanwhile, history continued along a different branch. And then they can decide later how to merge those two histories. So that's precisely what we can do within our applications, giving people the individual autonomy, just like individual developers have autonomy to work on their laptop without having to check back in with the central repository every time.
Okay, so this is very interesting. So essentially what Jinaga gives us is it gives us this the real benefit of this event sourcing is that we can recreate any typical state from any point in time. We can recreate it, so and everything's in one place, so it's very easy to keep track of everything, and things are usually pretty good. Maybe one of the downsides is if you want to verify that right now is legit, you have to go back and actually see literally everything and how it's created. And the advantages of Jinaga is it actually speeds up dramatically things like searching this graph, because you don't have to go through the entire history. You can just examine specific nodes pertaining to one specific bank account, for example, or a specific restaurant, or these types of things. So it increases searching and sorting. It reduces memory, right? So things are much faster, and you can see everything that applies to you just right here on your screen, and you can basically get on with this. Okay, so this is essentially what's happening from like a theory point of view. So would you be able to dive into this from the programmer or the software developer's point of view? What would this look like to build a system using Jinaga compared to the tried and true method? What does that look like?
Yeah, so with Jinaga, what you end up doing is every time you want to record a fact, you create an immutable record for that fact. In JavaScript, that would just be a JSON object. You just say, okay, this is all the information about what just happened, and you just say j.fact, and then it gets saved. In .NET, so I'm currently working on Jinaga.NET, that is literally a C# record. So it is literally an immutable record. It's pretty awesome. So that's the part about saving these facts. That's the easy part. Then in any system, you'll want to do things like update the screen. You'll want to notify other people who are interested in these things. You'll want to save it to a local database. You'll want to call an API so that I can save it to some remote database. You'll want to update some offline data storage. Maybe you want to offline update a search index. So all of these other things have to happen. So this is where the mathematics kind of comes back in, because every one of those things that you then want to do because you created a fact, those are things that can be derived from the structure of the facts themselves. So there's a concept that I call query inversion. So if I've written a query, that I'm going to use to update the screen. So, show me the list of all of the tables in the restaurant such that there does not exist a party seated at that table. So, okay, here's my list of open tables. Then when you seat a party, you expect that list to shrink by one. When a party gets up and leaves, and you bust the table, you expect it to grow by one. So those are different facts, different decisions that happen in the system that will affect that one piece of user interface. The way that we usually do that is a developer has to think about, oh, okay, this over here can affect that part of the user interface, and so I'll put that on a message broker, and I'll subscribe to iNotify property changed, and I'll do all these things in order to make sure that that happens. But the fact is, the information is already there in the query. The query says, tables such that there does not exist a seated party. So anything that causes that to change should update the user interface. And so you've written one query. The system can invert that query and figure out what are all of the different things that could happen to cause this to change. So that's one of the most powerful features of Jinaga, is that you right there within your application, you write your queries, it performs the query inversion, and then it just updates the user interface for you.
So this query inversion, this is the first I've ever heard of this. Essentially, what you can do is say, as a restaurant manager, I might say, to my host, how many open tables are there, right? And so then the host goes through and they run this complicated query of checking each aisle in each room, and they come back and they say, okay, we've got 10 open tables, right? And the inversion of that, would this be each table can, like the table itself can see the host, and when the host walks around, each table kind of raises its own little flag and says, hey, I'm available, right? I'm bored. I need people to sit on me or whatever.
Not quite. The inversion is that now the decision, the historical fact, knows about the user interface. So the decision to bus a table knows that causes the table to no longer have a seated party, and therefore will cause this that new line to appear on the user interface.
So rather than, because essentially what happens is often as a programmer, you're doing things, the dog barks or whatever, and in programming one of these things, like to bus a table, you might forget, oh, oops, you might forget to let the hostess know that something has changed, right? Surely there must be an incredible amount of things that I have to remember using Jinaga to make sure to update the hostess and to make sure that the manager knows. And like, how is this handled, if not by me? Who is doing this?
Yeah, that's the beauty of it. You express the intent. Remember, code is just intent. You express the intent that this list shows you, all the tables such that there does not exist a seated party. So that's the hard part about programming in Jinaga is flipping the way that you think about that, how you express that intent. So that's a very wordy way of saying here's a list of open tables. But if you remember to express it in that way, a list of tables such that there does not exist a seated party, then you give that intent to the system, and it can run a bit of mathematics on that. So I have a formal proof which appears in the book when I talk about query inversion, where if a fact affects a query, then this inverse query will exist that returns that user interface element when you give it that new fact. So this query inversion operation is completely mechanical. As a developer, you don't have to reason through all of the different use cases. No product owner has to write a user story that says when I bust a table, then the line no longer appears in the in the list of open tables, or now appears in the list of open tables. See, even just thinking through it, I got it backwards. So it removes the human element. It removes that degree of freedom. It removes that configuration of state that the machine could be in, that we don't want it to be in.
Right, the sloshing.
Yeah.
It essentially removes the ability for those cans to be sloshing around because they weren't defined. And if it just so happens that it's found that there is sloshing, the configuration can be changed to actually handle that new situation. Essentially, it's a bug, but now it's squashed because we actually we reconfigured. We looked at our the rules, the way the system is set up, and actually tweaked this, so this is no longer an issue. Okay.
Right.
So
and that's that conversation of I've expressed my intent. Now, computer, tell me if you understand my intent, and that kind of testing your intent. Did I really say what I thought I said? That has to be accomplished with a unit test.
See, so, I love that you brought it. So this is actually a very, this blew my mind when I was looking into it. It was actually so profound. And the reason is because the way, I don't really want to focus on the old way of developing, because this new way of developing, it seems very kind of natural. And so essentially there's like two kind of fields, or two, you can almost think of it as like funguses or something, that start here and they grow towards each other. And one of them is the configuration. So it's basically as it grows, it kind of defines what the system can do and what it can't do and all these types of things. And then you have the unit tests that are over here that actually expand with the thing. And the unit tests, it's like in the book GEB, Gödel, Escher, Bach, there is this really interesting idea of figure and ground. And it is that your house isn't defined by the struts or the studs or the drywall or whatever. Your house is defined by the emptiness that is within it, right? Or like day is defined by the night. So it's like there's the figure, which is like maybe the words in a book, or the ground, which is like the page itself, right? So nothing exists without the thing that it exists within. And so we have this kind of interesting dynamic here between the Jinaga state the configuration and these unit tests. So have I described that fairly?
Yeah.
What do you?
Yeah, I love that visual. Yeah, because I don't feel that I have truly explored a space if I just start from one area. If I just write a model and compile it and say, yep, it compiles. Yeah, I can prove some things about the structure of my code, but I can't prove everything just with that. But so I have to explore from this other direction. And so one direction is more of a statement of my intent. The other one is more of a statement of my requirements, what I want it to actually to do. Then does my statement of intent actually mean what I thought it meant?
This is fascinating. This is absolutely fascinating. What's so cool about it is because you almost don't even need let's say you only wanted to develop from the Jinaga point of view, right? So you define the system as you see, you declare your intent of what the system should do. And then even like somebody in plain English could even describe like, okay, well in this, like don't do that. Like they could describe the unit tests, or basically testing the system. Is it actually doing what it says it's doing? Like, what is the role of the programmer going to be in a world where this is the state of development, right? Where it seems that development teams would have to be much smaller than current because one man is so damn effective at building these systems with using this new methodology. We don't need these big teams, right? So maybe teams are going to shrink. Development time somehow with smaller teams is going to go down, right? We're going to be building software quicker. Like, what does the world look like when all we're doing is basically we're essentially not even writing code anymore. We're just declaring the intent. We're basically just writing almost plain English to the computer to tell it what to build for us.
Yeah, the world looks like VisiCalc.
VisiCalc.
Yeah. If you look up Dan Bricklin, I think it was Dan. Yeah, he worked with a collaborator. goodness, I forgot his partner's name. But yeah, I think it was Dan Bricklin who gave this talk where he's talking about the history of VisiCalc, and it's like during that period of time, you had COBOL programmers or Fortran programmers that could write a solid system and run some simulations, and then you had people who were doing analysis just on paper. And he's like, we're in this class and we're trying to do this analysis, and you know what? It would just be really cool to be able to write a system to do this analysis for us, but that takes a lot of work, and that takes this team of Fortran programmers, and we ain't got time for that. So they said, okay, what if we just taught a computer how to take the statement of our intent of, hey, this is the quarterly income, and then here's a formula that represents the amount of tax that I would have to pay on that income. And so that's just a statement of intent. And then if I can just take that and copy that over, and I do first quarter, second quarter, third quarter, always execute that same intent, let the computer figure out what depends upon what needs to be updated when. Now you've got this world in which a domain expert is also the programmer. A domain expert can sit down and write an Excel worksheet or VisiCalc worksheet. So yeah, I see that we have sort of a democratization of this capability, so that people with just the same set of skills that they need right now to use Excel can now take control of their own information and their own models, and then have that conversation themselves about their problem domain, and during that conversation, they're just collecting their information and putting it into a spreadsheet. But then that's executing the model that represents how they need to organize their information. But now this is where it breaks out of the VisiCalc or Excel box, is that it's no longer just one part, one file on their hard drive, but now that is a bit of intent that they can share with other people, and those other people can then build their own models, and they can start to collaborate. So yeah, I see having the domain experts with this capability. I see the information flowing freely from one system to another, with security in place, with rules about what information gets distributed and who's allowed to make changes. All that is in place within the model itself. But you no longer have data stored inside of a file, data stored inside of a database. You have data on the outside. You have data flowing from one domain expert to another, and executing according to their models and their intent.
So, okay, and just help me understand. So basically, from the perspective of the development team, there's actually now this inclusion of a domain expert. So instead of having just general developers who are able to build a backend and an API and all of these things to simply do the cookie cutter kind of boilerplate, the thing that's been done before, rather, because the system in a way, it just builds itself, like that part of it does it by itself. And so now we have the inclusion of these domain experts who are adept at declaring their intent of what the system might do or should do. Yeah, this might lead to so smaller development teams, more open communication. You alluded to the security concerns. So in a world where nobody trusts anybody, why would I want data from that other company? Like, what would be the use case of this?
Yeah, it would only come with an ongoing relationship with that company, with that that other party, and only to the extent that you allow that relationship to govern the information exchange. So yeah, for example, one of the ways in which I in the book, when I talk about security, I build security into the model, is that you then write a query that says, from this particular fact that I assert is true, here's a query that gives me back all of the users, all of the actors that that I say could assert that this fact is true. So very simple example is I publish a blog, so I can write a simple query. Here's a blog post. Who is allowed to write this blog post? Well, just this blog post is in that blog, and then this is the creator of that blog, so they're the only person. Or I could write a more complicated model that says anybody that this person gives authority to publish on their blog, and they do that by publishing a new fact to this this substrate. And so as a receiver of this information, I can run those queries and I can say, yep, that one checks out. It is digitally signed by somebody who has authority to digitally sign it. No, that one doesn't check out because the signature is invalid, or because my query says that they shouldn't have that permission. And so it's validated, it's verified on the receiving end. And so if I am if I am in control of the model that I'm running, then I get to write those rules and I get to determine what information I trust. And so that then that exchange builds up that relationship and builds up that reputation, which then will factor back into the model and let you perform more exchanges.
So, and I know we've discussed this before, but this really reminds me of Bitcoin, these blockchain. Essentially, it's a blockchain, right? So it's user verify, or rather listener verify, rather than sender verify, and everything is built up, and the trust is established over the course of time. And so you don't deal with people that are either not trustworthy yet, or have done something to but the thing is that if somebody tries to badmouth you or use your data incorrectly, everybody's going to know about it, because then that would be digitally signed and a part of the graph moving forward. So there's almost like there's no secrets. One of my biggest fears is software developers are going to be the first people out of work. That we're going to outsource our own jobs to our own work. Or so what do you think about that? Because it seems like
that's
you're taking a step closer.
Honestly, the need for software developers is so outpacing the rate at which we can train them that that's not going to be a near-term problem. In fact, the opposite is going to be the near-term problem. But long-term, this activity of expressing your intent and knowing that you got it right is a very highly skilled activity. So if it's not done in code, it's still done in some kind of code. But if it's not done in an imperative language where you tell it, okay, I want to put this message on the message bus, and I want to make this API call, and I want to parse this JSON, and I want to insert into this database. But if instead you're expressing your intent in a higher level of abstraction and letting the computer figure out all of those details, you're still expressing those intents, and you're still writing the unit tests to make sure that those happen. And so we will still need people that are highly skilled to partner with one-on-one, as you said, with the small teams, with the domain experts. For those domain experts that they themselves don't want to get skilled in Excel and write their own data sheets. They just want to say, okay, I'm going to run my business and I need you to produce this dashboard for me. So all right, let me understand the rules of your business. Let me document them. Let me have this conversation with the compiler. I'll also have the conversation with you, and we'll iterate. So I think the demand still far outpaces the rate at which we can produce people who are skilled at this. But that's where it becomes a human-sized problem. the demand was created by humans and satisfied by humans, and so the the economy of skill acquisition and employment is still what drives people need somebody who can actually write this code. I can figure out how to do that, and it pays very well because we're in high demand. So, all right, I'll transition into that. Versus, you know what? We're finding that a lot of people are learning this skill themselves, and so the demand goes down, the income goes down. I can find a better use for the skills that I've acquired by becoming a domain expert myself in something that I'm really passionate about. So I think people's interest in employment is going to move around in order to satisfy the demand.
And so is Jinaga just a natural step in this process that is ultimately going to lead us to a future where we think something and the software just writes itself, or the data just manipulates itself? Like, like where in the bigger picture of everything is Jinaga?
I have no idea. I have no idea. I'm an optimist. So I watch Star Trek and I think, yeah, that could actually happen. We could be in a post-scarcity economy. But I don't know. Maybe that's naive of me to believe in that kind of thing. But yeah, I believe that that this is one step into a future that the next generation is going to build, and I have no idea where they're going to take it. But this is the step toward what I think the future should be. And I truly believe that mathematics is the reason that we can have good things. That a lot of these things that you're talking about are enabled by the tool of mathematics. And so, yeah, sure, why not apply that tool to software, even software that writes itself once you've expressed the intent correctly, and then squeeze out some of those degrees of freedom, apply the right constraints, and see where society can take it.
Like, why is everybody? So where is Jinaga? Why is everybody not developing like this? Because frankly, it seems, from what I've heard and from what I've studied, it seems like a dramatic improvement to the current state of the art, which is hire a developer to do the thing that he literally just did for the other guy. It seems like software is very much a commodity. There's no difference between one piece of software and another. And so I don't know, but I'm very curious as to when we can see this and kind of where we are in the game plan. And because as a developer, I would love to use, it seems very cool to be able to use this exact thing that you're talking about. Yeah. So where is this?
Yeah. Yeah. So what currently exists is Jinaga.js, the JavaScript implementation of it, and I started Jinaga.js before I wrote The Art of Immutable Architecture. So I thought that I had it right. This book contains the mathematical proofs of the behavior of Jinaga.js, and as I was writing the book, I said, "Wait a minute, I can't prove this. This is wrong. Oh my goodness, there's a huge bug in Jinaga.js. It doesn't perform the query inversion algorithm correctly. It misses all of these cases." So I wrote the correct proof, and then right now I am in the process of going back and correcting the implementation in Jinaga.js. And at the same time, I'm also working with a partner, Jan, to create Jinaga.net. And so these two libraries are going to be interoperable from the perspective of you can write a client in JavaScript or a client in .net, and then they could each talk to a server written in JavaScript or written in .net and exchange this information. So I think the reason that we're not there yet is the same problem that I ran up against. I was able to get a lot done with the broken Jinaga.js. People are able to get a lot done with APIs and databases and object-oriented programming languages, and it's good enough. And good enough is the enemy here of this this possible future, where we actually do have to take the time to step back, write the proof, and then know that our implementation of that algorithm is correct and is going to solve the problems in the future.
Aren't you not worried that you're embarking on a journey that definitionally will never finish? Like, because of the way that math works and the way that these proofs are structured, like sometimes the only way to know that there is a way to know is to actually try. And then you could go down some rabbit hole where you figure out, oh, after years and years of this proof, it's actually impossible, right? So is this not worried you? You're not shaking in your boots at this point. There are things that your program fundamentally can't solve because of just the way that math works.
You already mentioned Gödel-Escher-Bach. So the Gödel in the Gödel-Escher-Bach was a mathematician who proved to us that a system that that doesn't have any a mathematical system that doesn't have any contradictions in it cannot be complete in that it cannot prove all true theorems. So there are some things that you could state, but you could not prove under this set of axioms. Now to jump forward to Alan Turing, you can't prove that this program will terminate, for example, but you could still write the program and it still might be a useful program, but you just can't prove these things about it. So that on the one hand seems like it's a it's a barrier to being able to accomplish what I want to accomplish, but at the same time, mathematics brings with it the conditions, the boundaries. So we talk about division. We know there's a boundary condition. You can't divide by 0, and so we just say, okay, that's undefined. Let's just make sure that we don't divide by 0 in our various problems. So in Jinaga, one of the things that you cannot do is to know that only one thing happened and not another. So take Bitcoin, for example. You have to know that if somebody has spent a coin that's in a wallet, that they didn't also spend that coin on something else. That's the double spending problem. And in a currency, double spending is a serious problem, and you have to find a solution for it. And so Bitcoin found the solution of proof of work in order to prevent double spending. Jinaga does not have a solution to that problem. So you cannot write a currency in Jinaga. So I simply say, okay, the math shows you what you can and cannot do. For those things you cannot do within this system, choose a different system. So if you want currency, there are still many other caveats going on in behind my head that prevent me from truly saying this and meaning it. But if you want a currency, go ahead and use blockchain, or go ahead and use Bitcoin. But for everything else, get off of that blockchain and use Jinaga. Yeah. So the double spending problem is one example. Let's take another example. So you might want to have a reservation system where you can reserve a particular room, or maybe you can buy a particular seat at a concert event. So you know that you have these 3 seats, not just any 3 seats at the concert, not just any 3 seats in the mezzanine section. Byzantine, that's a completely different conversation. The mezzanine section, but no, these specific seats, you have those. So they're non-fungible. There's the word of the day. So you have to know that somebody's sold you those seats and hasn't also sold those seats to somebody else. You have to know that somebody has booked this conference room at 3 o'clock on Wednesday, and somebody else didn't also book that same conference room at 3 o'clock on Wednesday. So if you are building one of those systems, and you use Jinaga, and the mathematics behind this is what I call historical modeling inside in the book. If you build a historical model of it, there are certain queries that you would want to write where you need a guarantee that this query returns only one fact. But you cannot get that guarantee out of the query that you've just written. So you have to tolerate the fact that every query could give you multiple results. And so if you find yourself in a situation where you say, I need it to have one, okay, you can't get it. Okay, that's where you go from the yin to the yang. That's where you say, all right, I'm going to build a different system that can guarantee only one. And so it doesn't have to be a proof of work system. It could be a centralized system. That's the other solution to the problem. So I could say, okay, I actually have a reservations database, and I have ACID transactions around that. So I can do a query in that database within a transaction and get 0 results. So I say, okay, I know that that room hasn't been reserved, or those seats haven't been sold. Therefore, I can do the insert in the same transaction, commit that transaction, and now I know that somebody else hasn't done that same transaction in parallel, said, okay, here's a 0, I'm going to insert, and now we get 2 records out of it. So, being able to put those transaction boundaries around a physical centralized database is one solution to that problem. Yeah, that is the power and the limitation of Jinaga, of historical modeling, is that you've got that power because you can act autonomously. You can know that if I make this decision will stick. I'm going to book this room. Okay, you've got it. It's booked. But I cannot know that somebody else hasn't also acted autonomously in a way that would contradict my decisions. And so if you have a non-fungible resource, if you have some kind of scarcity that only one person can do a thing, Jinaga cannot enforce that constraint.
So what about the most valuable constraint might be time, or who comes first? This was commonly called the Byzantine generals problem, and this is what this was the fundamental invention of Bitcoin, was that Satoshi solved this problem, and it's essentially, how do we keep our clocks synced up? Right? How do we know what came first and what came second? How do we do this without relying on a clock? Right? In Bitcoin, there are no dependencies really. Even on like clock, it's just so whoever did the work first, that's what propagates and things like this. So, and coming back over here, so this, are there any clocks in Jinaga, or so this all happens asynchronously, and so how is this order? Is this order determined? Like, what's going on?
The clock is that backward in time pointing edge in the directed acyclic graph. The clock is that the invoice is created after the purchase order, and that the payment is created after the invoice. So the clock is only a partial order. You can only tell that these 2 facts occurred in a particular order because they are causally related to one another. But if 2 facts are not causally related to one another, then you cannot tell what the order was. It doesn't assume that there is any universal clock that ticks forward for everybody at the same time.
And nor does it care, right? It doesn't. Right. It's totally irrelevant. Yeah.
Yeah, because that's one of the hardest problems in distributed computing, and when you try to solve that problem, you end up putting a whole bunch of inefficiencies into the system. So proof of work is a deliberately designed inefficiency in order to get a particular clock. And so even if you try to make an efficient clock by doing something like the Paxos algorithm in order to get some consensus, it's still a very inefficient algorithm. In order to get everybody to agree, you have to send a whole lot of messages before you can say, all right, now the clock ticks forward one more increment. Okay, send a whole bunch of messages. Now it ticks forward. But if instead you want that autonomy, you want...
Whoa.
somebody to be able to record decisions without waiting for the clock to tick, then you have to give that up. You have to give up the assurance that if I do a thing, somebody else cannot.
This is crazy. I don't know. I think that there's actually kind of a deeper philosophical meaning to this proof of work stuff, which the thing about these, some of these cryptocurrencies is that they only have value because they're copied. Like in this digital realm that they're in, there's really no work to be done, right? There's no, like traditionally value comes from a human being putting their effort and their time and energy and attention into a specific thing. May that be digging a hole to pull like gold out of the ground or something. And so throughout all of human history, you have to expend work to get value. This is how it always has been. This is why using gold as money is so strong, is because the gold represents the work that you did, you know?
Yeah. Yeah, it's proof of work without having seen that work happen. It's like,
right.
Oh, this gold must have gotten here somewhere. Somehow somebody did a whole bunch of digging.
Yeah. Right. Exactly. And going over to this idea that you're talking about, it's the fact that the transaction happened proves. I'm trying to kind of connect this.
Yeah, really the things that make it different. Blockchains have a really awesome set of solutions to problems that have emerged. The only thing that's different is that the blockchain, there's more than one blockchain, but the blockchain is a linked list. It's a data structure, and it's a linear data structure. When you add a new block to the end of the chain, somebody else could add another their own block to the end of the same chain, and it would fork. And then proof of work says no. We are going to build on one and not the other, and whichever one we build on, that's the one that we take to be truth. And so it chops off those forks, and when you look back in time, you just have one chain. Ethereum forking, all that aside, but so the big difference here is that it is decisively not a chain. It is a directed acyclic graph. And the reason for that is that if I buy a coffee with Bitcoin, then the person who sold me that coffee has to wait for 3 or 4 blocks to be added to the chain to have the confidence that the transaction actually went through. If they see one block, it's not enough, because another block could be coming right behind it that was not built on theirs. And so you have to go back to the blockchain in order to make sure that these transactions committed. So you don't have the autonomy to just know that a decision I made in isolation is going to be honored. So yeah, that's really where the difference is. It's not linear, it's a graph, and it's not totally ordered, it's partially ordered.
And the third thing might be the value that, because essentially you're building a blockchain. It's essentially a blockchain. A little bit of the same advantages, a little bit essentially it's kind of a blockchain. 2 questions: when is the ICO, right? When are we going to tokenize this? But like in a proof of work thing, you mine and you get value, right? You get you get some scarcity. Whereas in this directed acyclic graph scenario that you call Jinaga, instead of value, it's computing power, or it's the order of the computing power that we're kind of racing for.
It's the information. So there is no scarcity built into it. Yeah, that's another good description of proof of work, is that it is a deliberate scarcity generator, and the work that you're doing is literally just computing hashes of random numbers until you get hashes that begin with zeros. Right. It's meaningless work. I mean, it is mind-numbing. If a human were doing this work, they would quickly do something else. They would dig a ditch, because that's far more. And
people do dig ditches for gold, right? This meaningless yellow rock, and people still do it, right?
Yeah. So we had to invent work for the computers to do in order to make this algorithm work. So if we imagine a post-scarcity world, which I am naive enough to believe will actually happen, then scarcity isn't what creates value anymore. It's information. It is autonomy. These things have value in themselves, and so Jinaga is a way for people to exercise their autonomy over their information while they're collaborating with other people. That's where value comes from.